Good morning, everyone. Today, I will be talking to you about the storage tanks and transfer lines for cryogenic fluids. There may be a slight overlap between the earlier lecture and this one on the design of cryogenic system, what we had discussed a little earlier, one of the earlier talks. But it does not matter because specifically there is a mention about the storage tanks and transfer lines for cryogenic fluids in your syllabus. So we will discuss about this. Okay. Okay. Now, what is the plan of my talk is like this. We will talk about introduction to storage vessels, the small and large storage containers, the various components that go into the fabrication, the materials which are used for construction, how do you determine the wall thickness, okay, supports and suspensions, and then piping in the cryogenic systems, the choices of thermal insulations, and then the evaporation rate of cryogenic vessels, cryogenic containers. How do you fill, drain, and vent, and the various instrumentation. We will also discuss about the transfer lines for cryogenic fluids. Particularly, we will try to see how does one fabricate a transfer line, what are the steps involved. We'll just have a brief discussion about that. And then the transfer line couplings and the cryogenic walls, and we'll conclude this talk. Okay. Uh, Regarding a storage system for cryogenic fluids, one should think about the following: whether the storage is for a short term or a long term storage of the fluids, what is the liquid which you are going to store, okay, and what sort of evaporation losses you are expecting on the system. Will it be stationary or will it be mobile? If it is mobile, what are the acceleration loads that are anticipated? And overall, the cost which is involved in making such a system. Okay, let us start with the small size storage containers. Uh, if you look at the small size storage containers for cryogenic fluids, generally they are all vacuum insulated. And in fact, the very first storage container for cryogenic fluids is glass storage containers. Okay. So you have one inner vessel, you have an outer vessel, and that's a total system which was used, and the interspace was evacuated. Of course, nowadays you have the glass storage vessels up to certain volume, not very large sizes, and you also use, uh, the instead of to cut down the radiation heat transfer, you coating, of the inner surface is done with highly polished surfaces are made inside, so that you will be able to get the system which can also take care of radiation heat loads. Ideally, one would like to have it spherical in shape, so that the inner vessel is supported from the outer vessel from the thin wall neck of the maybe of stainless steel, or if it is a FRP neck, then the vessel will be of aluminum constructions. Perhaps you may also require some lateral supports. This is just to avoid the relative motion of the inner and outer vessels, but certainly not 100% mandatory. Okay, the inner walls are polished to obtain low emissivity, so that the radiation heat transfer is significantly reduced. If you have a super insulated container, then uh, instead of having um, just the slight polishing of the inner outer inside of the outer surface and outside of the inner surface, Okay. You also have, sorry, you also have radiation shields of low emissivity, which are mounted over the inner vessel. This takes care of the radiation heat loads that are coming from outside, and the interspace is evacuated using a suitable arrangement to the level of something like 1 into 10 to the power minus 5 millibar pressure. In the case of vessels which are using liquid helium, you normally have also a liquid hydrogen shielding. Okay, either the direct liquid hydrogen shielding or refrigerator shielding are used. We know that these sort of systems will have operation rates from about 2 to 5%. But the shapes of smaller containers are certainly not suitable for large storage containers because you cannot make it into the so-called spherical shape. You have to modify the shape such that it becomes a cylinder with the dished ends on either side. Okay. Okay. So when you come to larger storage tanks, you can see the picture and gives you an idea of how the storage tanks looks like, the internal structure. First of all, it has an inner vessel and an outer vessel. See, unlike the small size storage container, the inner vessel cannot be suspended from the neck of the outer vessel. You require special support arrangements so that the inner vessel gets supported with respect to the within the outer vessel. Okay. Now, many times, depending on the size of the cryogenic container, you also have an access manway which is sufficiently big so that a person can go inside and do whatever cleaning or any modifications internally which need to be done. It can be done. So that depends on the size of the container. Okay, so access manway can be done, which connects the inner and outer vessel. You certainly require pipes for filling and venting, and also many other instrumentation aspects. When I talk about instrumentation, what I mean is, for example, I want to measure the liquid level quantity. So for that, I can think of having hydrostatic pressure measurements. That is, measure the pressure at the top of the liquid and then at the bottom of the container. Then you will be able to find out the hydrostatic head, and from there determine how much quantity of liquid is present in the system. Many times, if they are big containers, then the pressures at the surface has to be distributed equally at all locations. So you think of having a vapor diffuser arrangement, and that vapor diffuser will make sure that the pressure is more or less uniform at all these locations. Okay. Depending on the container size and its utility, one has to choose the right insulation. For example, super insulation can be one of the best insulation that is available for this one. So you can use super insulation along with the high vacuum, and with that, you will be in a position to have a good performance of this system. Of course, there are needs for safeties and instrumentation aspects. So you require externally, when you are to draw the liquid, you require a vent valve, the liquid fill and drain valves, and also you have to have a vent valve and so on. Okay, and if you are measuring the liquid level through the hydrostatic head, then the ports have to be connected to the hydrostatic gauge. Differential pressure gauge has to be used for the measurement of this. Okay, and that has to be calibrated from 0 to 100%. Okay, this needs to be done. Okay, what about the construction materials for the cryogenic systems? As this we have already discussed, but anyway, I just have a brief repeat of this. First of all, materials of construction should not become brittle at cryogenic temperature. So 304 austenitic stainless steels, 18% chromium and 8% nickel, that they are quite suitable. Copper and its alloys, brass, Everdure, which is an alloy of copper, nickel, and manganese, can be useful. for construction of the cryogenic systems. Aluminum and its alloys, maybe 5% magnesium, small quantities of manganese and chromium. And then you can also use titanium and its alloys. They are essentially useful for weight reduction. Okay. And for special applications, you can also use alloys such as inconel, iconal, and then iconal X, monal, everdur, etc. have been used. Okay. Now, wall thickness of the vessel which one is fabricating has to be determined. Uh, we have given a detailed description of this in one of the earlier lectures when we talked about the design of cryogenic system. But anyway, for the sake of completion, I repeat this here. It has to be calculated using the ASME pressure vessel code section 8. Unfired pressure vessels or equivalent standards, British standards also can be used. The inner vessel is designed such that it withstand the internal pressure to which it is subjected. Okay. So you have to also introduce the factor of safety in all these cases. Okay. Whereas the outer vessel, it is designed based on the collapsing pressure. That means an external pressure, whatever that is coming in, can make the system buckle. So normally in most of the outer vessel, the pressure difference will be only 1 bar, but there will be a factor of safety, maybe 3 or 4, that will also be involved with this. Okay. The outer vessel can be fabricated either from stainless steel or from carbon steel for big capacity vessels, because stainless steel fabrication may be quite expensive. So one can look for mm, either carbon steel also can be used, but one has to make sure that wherever there are cryogenic fluid entry is there in those zones, it is not carbon steel. That is, you should have stainless steel in that zone, other because carbon steel undergoes a ductile to brittle transition around 100 Kelvin. Now, to minimize the weight of this vessel, one can start with the thin sheets, but provide adequate stiffening rings over the various sections. So that also is another option that is available. So this is essentially done to minimize the. Now for the wall thickness, just for the sake of completion, let me run through this. We'll discuss a method adopted for determining all the thickness of the cylinder, the wall thickness of the cylindrical shells. First, it is to be determined whether it's short cylinder or long cylinder. Okay. So there are formulas which will tell you whether it is this criterion is met, then it's a short cylinder, or this criterion is not met, it's a long cylinder. Then based on the collapsible pressure, okay, one can determine the wall thickness. Okay. And so you get the outer diameter of the vessel can be determined using the operating pressure and the weld efficiency and maximum allowable stress for the material, etc. Okay. And similarly, the wall thickness based on bursting pressure is also given by another equation, okay, which is described here. So here you use the Young's modulus, Poisson ratio, and the wall thickness of the shell, etc., are used, and then you calculate. The same thing, a similar type of calculation can also be done for the distance, wherein the wall thicknesses may be somewhat smaller in such cases because of the already it is taken elliptical shapes. Okay, let's move on to supports and suspensions. As you know, compared to the vessels, small capacity vessels, the bigger vessels cannot support. The inner vessel cannot be supported within the outer vessel. Inner vessel cannot be just suspended from the neck of the outer vessel. You require special support structures. So some of the support structures are, for example, vertical support structures, and then lateral support structures are used. You can see here the vertical support structure here, and then the lateral support structures are used. Okay, these are the things which are required for big capacity storage containers. And also, if in some cases you require longitudinal support structures so that the inner vessel is more or less centrally positioned with respect to the outer vessel. Okay. And at the ends, you normally use springs such that the inner vessel does not come and touch the outer vessel. Okay. Now, the support structure should be such that the length of the support structure should be long, its cross sectional area should be small, so that the heat transfer from the ambient to the cryogenic tank, inner cryogenic tank, is minimal. Okay. Now, there are number of designs which are available. I think more details are available in Randall Barron's textbooks on cryogenic systems. Uh, for a LOX system, liquid oxygen storage system, under a project with HAL Bangalore, IAC has also designed and fabricated and used a special, you know, supports arrangement like this, which is shown here. And this support arrangement uses a fairly long length of rod because, first of all, the concept is that it should have enough strength and also have long length of heat transmission. That is from the outer vessel to inner vessel. The path length of the heat transmission is quite long. Okay, so the arrangement is like this. From the room temperature, you have a supporting arrangement through a spring. This vertical solid rod goes to the bottom, a swelling, washer here, and then it rests on a SS pipe, stainless steel pipe, and then which is supported on the inner vessel. So the heat transfer path is from here to the swelling nut, and then to the pipe, and then to the inner vessel. So the path length is fairly long in such cases. These sort of support systems have been successfully utilized on the liquid oxygen storage units which were developed at our department at IAC, and they were successfully tested. For example, the inner vessel was filled with large quantities of water instead of cryogenic fluids, of nitrogen, and then on the road it was moved and tested for its performance. It worked out to be quite satisfactory, and so this sort of design has been used in all the cryogenic tanks which have been developed towards the lock storage. Okay, let us come to the pipes in cryogenic systems. The pipes are needed for filling, draining, and venting the cryogenic fluids. Okay, when you vent the vapor of the cryogenic fluid and the vapor of the cryogenic liquid, and when you fill, you can either do a filling from the bottom side or from the top side. If you want to completely empty the vessel, then you will require a special drain port also. Normally, the liquid level monitoring can be done by different methods. One of the very standard method is to use a differential pressure arrangement in which you monitor the hydrostatic head of the liquid column. So you actually what you have is you have two lines running from the inner vessel to the outer vessel. One is taken from the top where you have it sees only the vapor. Okay, another one is taken from the bottommost point, which it sees both the vapor as well as the liquid. So the differential pressure will read the pressure of the liquid column, vertical hydrostatic level of the hydrostatic pressure of the liquid column. And since you know the density of the fluid, you can calculate what is the height of the liquid inside the cryogenic tank. Now, methods for filling are, for example, gravity filling in cryogenic vessel. Uh, it has it will have a direct access to the inner vessel through the bellow connection from the top, so you can connect it up and then so that it can be filled in. Okay, or if you are looking for alternate filling arrangement like pressure filling, then it can be connected either at the top or at the bottom through the appropriate pipelines. The pipes, cryogenic pipes will be normally made out of stainless steel. Sometimes one can also use copper and also nickel alloys. But in all cases, one has to take care of the thermal contraction when the liquid is flowing in, because you have a liquid flow from inside to the outside. During that time, that can be thermal contraction. And during the thermal contraction, there will be a lot of strain between the places where the joints are made. Okay. For this purpose, the pipes are either bent or sometimes they are looped so that it can take care of this thermal contraction. Okay. What about the insulation of the cryogenic tanks? The choice of the insulation for cryogenic tanks depends on the cryogen what is being used. It can be divided into two groups. So the group A will have liquids whose boiling points are between 77 and 185 K. Mostly the liquids like oxygen, nitrogen, argon, etc. fall into this category. And then in group B, you have liquids whose boiling points are below 77 K. Okay. Here you have helium, hydrogen, and neon. And group B liquids are more expensive, cost more to produce, and also they have lower latent heats. And so essentially one uses multi-layer insulation for these cryogenic fluids. Okay. So group B vessels will be generally made out of multi-layer insulation. Multi-layer insulation can also be used in cases where you require a low loss rate, and sometimes the weight can become also a prime consideration. Otherwise, other type of insulations are okay for many of the storages. Okay. Now let's just look at the different type of insulation. High vacuum insulation used for small vessels of liquid nitrogen, liquid oxygen, and for liquid helium with the LN2 and LH2 shields. Okay. Coming to evacuated powder insulation, it is used in large scale uh, group B liquids and small scale group B liquids in a small scale in a piping stationary vessels of any size. Okay. Uh, Coming to the MLI with vacuum, multi-layer insulation with vacuum, used in small liquefiers of Group B, liquid vessels of Group B, transport vessels of 10 to 20 meter cube, stationary vessels up to 1 meter cube of Group B. Okay, other than this, there is also something called microsphere insulation. I think this is discussed in the topic on insulation. Microsphere insulation is nothing but a small glass, spherical glass spheres, uh, which are coated, okay, and they are hollow spheres so that the heat transfer will be minimal. The solid conduction heat transfer will be minimal, and they are useful for small and medium sized vessel where the application of MLI causes a lot of difficulties. So microsphere insulation also has been used in some cases. Okay, now let us look at the evaporation rate as a function of size and shape. Heat influx into the storage vessel decreases with the surface area per unit volume. Okay, so optimal shape, therefore, will be spherical. This is what we have said already. You should have a spherical shape because the sphere has the lowest surface area per unit volume. And so small vessels can be made of this particular shape. But when you go to higher capacity vessels, vessel size of the order of 0.1 to 100 meter cube, etc., they are made cylindrical with the ends as distance. Okay. So it can be either vertical or horizontal. That depends on the user's requirement. The shape increases. This particular shape of cylindrical geometry with the distance increases the specific surface area per unit volume by approximately 10%. Okay. So, but it has the advantage of fabrication, fabric, and also the transport. Okay, all these things can be really taken care if you modify the shape like this. Now, the evaporation rate of cryogenic tanks, for example, can be normally it usually decreases with increase in the vessel capacity. So you can see here it is G is equal to a constant divided by V to the power 1 by L. Okay. Here G is the quantity which is lost per day in terms of percentage, and V is the volume, and C and N are constants. So you can see here there is a plot. Uh, Percentage loss, the I think the y-axis is in logarithmic scale, x-axis also is in logarithmic scale. So, but you have straight lines. Okay, 1, 2, 3, 4, etc. That's what you get. So, the operation rates are determined by the heat flux by supports, pipings, etc. In the case of large systems, the evaporation rates are determined by heat flux by through supports, pipings, etc. In the case of large systems. The the graph shows you the behavior for use of high vacuum insulation, number one, evacuated powder insulation for in the case of oxygen, nitrogen, number two, and then evacuated perlite for oxygen, nitrogen, number three, and MLI systems, number four, and also the MLI system for hydrogen, number five. So you can clearly see once you start using MLI, the operation rate sort of seem to improve. Okay, okay, with the sort of okay. What about filling and draining of the cryogenic fluids? How do you do that? In small capacity containers, it can be filled by just gravity. I mean, maybe one can just take the container, lift it, and then pour the liquid into whatever that you want to fill in. Okay, it's just drained by the gravity. On the other hand, in the case of bigger vessels, you need to have a pressure filling or pressure transfer, either for filling into the container or draining out of the container. You can also use special pumps. Cryogenic pumps can also be used for filling from the storage, from the low pressure storage to high pressure. And special transfer lines are needed for this purpose, okay, for filling it. Let us look at the instrumentation here on a cryogenic tank. So you can see here you have an inner vessel, you have an outer vessel. Then there are many things what you see here on the top of instrumentation. So first of all, you have a vent valve which allows you to the vapor can be vented out, and you can see the pressure on the top of the liquid by using this pressure gauge. Then the interspace vacuum can be measured by the vacuum gauge. Okay, and you can also use a, a parallel line or another line to evacuate the interspace. Then you have the differential pressure gauges, which can one give you the percentage of content that is available here. So this lines wherein you measure the hydrostatic pressure using a differential pressure gauge. Then you have a bottom fill line with a suitable wall, which has safeties, namely the bursting disc, safety valve, and then the bursting disc. And also the top filling line, which has a suitable valve, and then the bursting disc and safety valves. Okay. Now, normally, you also have something called pressure raising valve, which enables you to self-pressurize the cryogenic tank. That means you take a small part of the liquid from the inner tank, and then allow it to come to in contact with room temperature, so it vaporizes, and the vapor returns back to the that evaporating that warm up vapor returns back into the vapor space over the liquid of the inner container, and then thereby it increases the pressure. So this way, you don't require an external pressurizing agent. So these type of tanks are called self-pressurizing tanks. Okay. So you will be able to make use of it for a continuous transfer for many times in terms of experiments and so on. Okay. Okay. I think this is good enough for our discussion on cryogenic storage tanks. I will now discuss on transfer lines. See, the transfer lines are very much required for the cryogenic fluids. You transfer the fluids from one region to another, and you require the cryogenic transfer lines. The transfer lines can be made up either rigid line or flexible transfer lines. Sorry for the interruption. Hello, welcome back. I will talk to you now about the transfer lines for cryogenic fluids. Transfer lines are required to transfer the cryogenic fluid from one region to another, maybe one storage to another storage container, or one storage to the experimental cryostat, etc. And this is essential because we would like to see that the required the experiment requires the cryogenic fluid and it is adequate quantity is transferred for that purpose. The choice of the transfer line depends on the type of transfer and the such as a small quantity of for a short time, or let's say large quantity, or you are going to transfer for long distances, etc., etc. So depending on that, you can select the type of transfer line which you would like to use. There are two types of transfer lines. Basically, you have what is called the rigid transfer line, and then you have what is called flexible transfer line. Rigid transfer line has got fixed dimensions, and they are made out of rigid tubes. And whereas the flexible transfer lines are fabricated using bellows. Okay, both the inner one and outer one are made of bellows. So you can see in the photograph, you have the rigid transfer line in the upper part of the photo, the upper photo. The lower photo shows you the flexible transfer line. Okay, now coming to the different type of transfer line, let's say uninsulated line. The uninsulated generally used for small quantity transfer and also short distance transfer of particularly the cryogenic fluids like liquid nitrogen, etc. Of course, liquid helium you cannot transfer at all. You certainly require a vacuum insulated transfer line. And for vacuum insulated generally are useful for large quantity transfer, for a longer length, etc. So vacuum with MLI is also very useful for several applications. Okay, so for experimental systems transfer, etc. So continuous transfer for long lengths and long times, they are quite useful. First of all, when the fluid is transferred through the transfer line, there is a flow of heat from the transfer line into the fluid, and this causes a vaporization of the fluid that is going through, and therefore you have what is called two-phase flow. That is, you have a vapor and liquid flow simultaneously occurring. Okay, now because of this extra heat that is coming in, it actually reduces the quantity of fluid that is transferred to the other end. So at the inlet, you may have some X quantity that is coming in. So whereas the what is going out will be now X minus something. Okay, because of the loss by the vaporization. Okay, let us look at the transfer lines, uninsulated transfer line where all they are used. For example, uninsulated transfer line used for liquid air, liquid oxygen, liquid nitrogen, pressure transfer for short distances. That means all that you use a simple pipe, connect it from one end to the other. So and then through the pipe, the liquid is able to flow. For liquid hydrogen and liquid helium cannot be transferred in this manner. You certainly require vacuum jacketed systems. So uninsulated lines are suitable only for liquid air, liquid oxygen, and liquid nitrogen, and particularly for short distances. What about vacuum insulated line? Appropriate for efficient transfer of liquid nitrogen, liquid helium, liquid hydrogen, liquid oxygen. Okay, very efficient transfer of the cryogenic fluid can be done using the vacuum insulated line. There are several types possible. Okay, vacuum insulated types, several type of vacuum insulated transfer lines are possible. The design of transfer line is exactly similar to that of the cryogenic container or cryogenic storage vessel. You should also take care of the thermal contraction during the transfer because the inner line will become cold, so it will try to contract within the outer line, so causing strains in the joints. Okay, I will briefly touch upon the fabrication of the cryogenic transfer line. First, suppose you want to make a transfer line, what are the things you have to worry about? First, decide whether you want to have a rigid transfer line or a flexible transfer line, and also select the material which you are going to use for fabrication. Okay, selection of the inner line will be based on the design throughput. For example, how much quantity has to be transferred through the transfer line. So, based on that, you will be selecting the diameters of the line. The outer line diameter will be based on the insulation which you are going to use over the inner line. Okay, so depending on, for example, if I'm thinking of a powder insulated transfer line, then probably the thickness will be much higher. Whereas if it is a super insulated transfer line uh, with the appropriate evacuation port, then the outer diameter will be somewhat smaller. Okay. Now, you should also decide on what should be the end connections of the transfer line. Maybe you certainly require rigid end connections on either side. Okay, because suppose I want to transfer liquid helium from my storage container, liquid helium storage container to the cryostat, then I require rigid sections both which go into the storage divar as well as into the cryostat. So that is required. You also may require instrumentation of the transfer line uh, if you so desire. I'm not sure that every time you require the instrumentation, but in some cases you may require instrumentation for monitoring some purpose, something. You may require the instrumentation, but maybe some temperature of the inner line to be measured or something like that. Then you also have to decide on the spaces uh, which go in between the inner and the outer lines. What sort of spacer you have to use? Normally, low thermal conductivity spacers are to be used. And if you are using bellows to take care of thermal contraction, it is preferable to use it at the outer side, on the outer part of the tube, on the outer tube, not on the inner one, because it is much easier to repair or make any modifications in case it's needed. Another important aspect is first decide on the detailed fabrication procedure. Please understand that every joint that you make has to be leak tested. Okay, you have to make sure it is leak tested and also sometimes pressure tested and so on, so that it is totally leak tight right from the start till the end. Okay, then the transfer line, you should also decide on what is the insulation which you are going to use, or for example, are you going to use let's say for example absorbents on the inner line. Sometimes you may need them to make sure that the integrity of the vacuum is good, and also sometimes you may use getters to take care of the hydrogen evolution from the stainless steel parts. Okay, so some of the things like this you have to really take care of this. Okay, now the schematic of the rigid and flexible transfer lines is shown here in this diagram. So you can see the inner line, and then you have the outer line. The outer line has got a bellow which takes care of thermal contraction. Okay, and you will have an appropriate vacuum port. for evacuation and so on. Okay, and you require also some spaces which will make sure that the inner line does not touch the outer line. Okay, which will be low thermal content space. Now, this diagram below shows you a flexible transfer line. In a flexible transfer line, the thermal contraction part is automatically taken care because you are using flexible line, that is bellows you are using for both the inner and outer. So therefore, the thermal contraction part is automatically taken care in this case. Okay. Some of the spacer designs for the transfer line is shown here. You can think of a triangular shaped spacer or a square shaped spacer, which touches only at specific points on the outer one. And you can also think of roller type of arrangements uh, of the inner vessel getting suspended on the outside on the outer vessel. Oh, sorry, inner line getting suspended on the outer line. Okay. I would like to show you some small examples here of transfer line which have been developed in our laboratory. For example, here, this is an instrumented transfer line. So the inner line is a bellow line, and these are the spacer locations. You can see that dots things here, spacers, and this is inserted into the outer line, outer bellow. So this is the outer bellow part. So when after doing this, you have the total assembled system of a transfer line, which is shown here in this diagram. Okay. Now, normally after fabrication of the transfer line and then the interspace evacuation, etc., you need to perform experiments to find out the performance of the transfer lines. Okay, how, what about its cool down, how much liquid it is able to deliver, etc., etc. So for this, you require a dedicated experimental setup. So you have a storage vessel, uh, supply storage debar, and the receiver storage debar, and the transfer line is mounted in between. And of course, you have pumping units, etc., for evacuation of the transfer line during its fabrication. Okay, and this system can be instrumented for void fraction measurements, etc. And by applying a known pressure on the inlet storage devar, the liquid will be transferred to the and then collected at the outer storage vessel. Okay, receiver storage vessel, right? If I are looking for transitions or joints between the transfer lines, then you require what are called bayonet type couplings. And this figure shows you the bayonet type couplings between one transfer line, one part of the transfer line, another part of the transfer line. These special designs ensure that the outer jacket is maintained room temperature while the inner line carries the fluid. The thermal contraction of the inner tube is also taken care. Liquid flooding at the warm end is normally minimal. So bayonet coupling and the field welded joints are quite normal, quite normally used in the design of the transfer lines. Okay. Coming to briefly touch upon cryogenic walls, you have different type of cryogenic walls, extended stem walls. The walls which normally handle is maintained at ambient temperature. Then sometimes you also have vacuum jacketed walls. The extended stem wall is surrounded by a vacuum jacket, and the wall seats are made of either copper or Teflon, depending on the supplier. So they are quite useful for it. So what we notice is conventional shapes of all the walls are also used for cryogenics, except for the fact that the operation zone is maintained at room temperature by the extension of the step. Okay. In conclusion, I would like to mention that the storage systems and transfer lines are of prime importance for using cryogenic fluids for their long-term storage and transfer of cryogenic fluid from one system to the other. The choice depends on the specific application along with the cost, and a lot of details are available in the reference textbooks, and one has to go through that to find out if you want more information on the development of cryogenic transfer line. I sincerely thank you for your patient listening. Um, okay, have a nice day. Good morning, everyone. Today, I will be talking to you about the storage tanks and transfer lines for cryogenic fluids.